What happened, Manish?
Sir, Monday का है क्या quiz?
Mondays will be the quiz. Yes, the same time. I will send you all the details instruction. Okay.
Okay, sir.
Okay. Can you see? And syllabus I will send you to today's lecture. Until today's lecture, the syllabus is okay. Lecture 7. Today is the lecture 7. So this is the until this much the syllabus is. So can you see the white page? Hello. Can you see the white page? Okay.
Yes, sir.
Yes, sir.
Good. Okay. So let us recall a problem. So this is the last class for the first order. Okay. Let us recall a problem. Consider the problem. Uy plus ux equal to 0. Okay. X belongs to R and y positive. And u of x naught is hx, which is discontinuous. That is 1 when x is less than 0, 0 when x is positive. Okay? Okay. The characteristic curves are what are the characteristic curves? Anyone remember? X equal to hs into y plus s. So what is hs? This is like this. Y plus s if s negative and s if s positive. So the speed of the curve is dx by dy is hs. So this is 1 if s negative, 0 if s positive. So what is the characteristic? This characteristic looks like this is x, this is y, this is for s negative, this is s positive. Okay. So until s negative, you just see s negative, the speed is 1, and of course this is the equation of a straight line. So this is like this. Okay, and s positive we have yes. So the characteristic lines intersect for all s positive. That means here for s positive in this space, all the characteristic line intersects. Now the question is, if the characteristic line intersects on those points, you have a problem in defining the solutions, classical solution. The question is then how to define a solution. Define a solution, because you know that whenever characteristic line intersects you cannot define classical solution. You know what is the meaning of a classical? That is a C2 solution, classical solution, smooth solution, pointwise sense solution. So we need to define. So for this type of cases, when the characteristic line intersects, we need to define a different notion of solution. A different notion of solution, which is different from the classical sense. Clear? Is that clear? You know, whenever you remember this example, whenever this intersects, the solution is discontinuous. You know all those things. Okay. Then the question is how to define the solution. Any idea? Can anyone tell me how to do that? Yes? Any idea? Can anyone tell me how to do this? Huh? What happened? So there is something called weak solution. Okay? Which is a different notion than a classical solution. Okay? Okay. We shall study weak solutions of the following initial value problem. Of the following initial value. This concept of weak solution is very general, but let us confine with just a particular class of problem. That is the first order. Okay? So UT, consider the problem, f of u x equal to 0. Okay? T positive and x. This is your equation 1, I say, and the initial condition I say u at x0 is equal to h of x when x belongs to. This is condition number 2. Okay. Where f from R to R is given to be continuous, is a continuous function. Okay. So we want to study, this is a problem, okay? We will come, f is just a continuous function. You understand? Is that clear? So u is a function of x comma t. Okay? U is a function of x comma t. T is a positive, that means we want to study. This is your domain. This is your domain. And the solutions ux naught, the initial condition is given as usual at t equal to 0. This line. So this is your domain. So you want to the equation is given in this space. You want to study how to define a weak solution. Okay, and f to be given to be a continuous function. Okay, just a motivation before formally defining a solution. Let us give you a motivation. Okay. So what is your equation? This is very simple. The idea is very nice. Ut, the equation is ut plus f of u derivative f of u whole, you can understand. This is what is the meaning of this. F of u equal to 0. This is your equation. Let us suppose first case. Let us suppose u and f are both smooth function. Let us assume smooth function. That is you can define pointwise like a classical solution or a classical. Use a classical solution. Let's say classical, and f is also smooth. So everything makes sense here, pointwise sense, right? Because u at xt, this if you at xt, everything makes sense. Okay, clear? Now let us consider. This is just a motivation part. Okay, let us consider a function v from R cross 0 infinity to R. Okay, so the domain of V is this. Full stop, including this part also. Okay, this is your domain of V. Okay, let us consider VCC infinity is a smooth function. Okay, it's a smooth function with compact support. Anyone know the meaning of that? With compact support. Who knows the meaning of having a compact support? Huh? Who knows the meaning of compact support?
Basically, the closure of the set of points where V0 is compact.
A function, just a general definition. This is just a definition. Let a function f from x to r. The support of f, x is any subset of Rn, anything. Okay, Rn or something. Okay, or any this type of zero velocity. Support of f is defined as set of all x belongs to the capital X, where it is defined such that fx not equal to 0, and take the closure of that set. Okay, this is called a support of f. So what immediately you can say, support of any function is what type of set?
Closed.
Always closed. Always closed. Now I am saying it has a compact support. What does it mean if we are working in subset of Rn? What does it mean? Huh? What does it mean? You have already a support of exactly plus bound. But of course, this is not a general definition of compactness, you know. But since we are working in a subset of Rn, this is okay, right? Closed plus bounded imply compact. Is that true? Is it correct? Yes or no?
Yes, sir.
Okay. So with a compact support means the function. What is the meaning of that? That means the function is non-zero on a compact set. Outside the compact set, it is 0. Clear? So like this. Suppose there is some set in this domain where the function is non-zero. Of course. Can you tell me what will happen at the boundary of that compact set? What happened? What can you say about the functional value at the boundary point of that compact set? What happened? Can you say, what can you say about the functional value at the boundary point? Huh?
Well, if the function is continuous, then there must be 0.
It must be 5.
Because the boundary points can be we can find a sequence of points convergent to the boundary point. So by continuity, they must be 0.
Yes. So the boundary point, the function, that compact support if I say the support is compact set K, the functional value at the boundary point, compact set means closed and bounded, so it contains a boundary set, boundary points. So that point, at that point, fx has to be 0. So you understand what is the meaning of that. Okay. So I take any compact set in this domain, okay, r cross 0 infinity, okay, with a smooth function which is compact. Okay. Now what I will do, what is your equation? Ut plus f of u x equal to 0. You multiply this equation with v of xt, that function. Let us consider v of xt with this function. If you multiply and integrate, what will happen? If you multiply and integrate, you will get minus infinity to infinity. The domain is 0 to infinity. Ut v plus fu x into v of xt dt dx equal to 0. Multiply with vxt and integrate. Integrate. Okay? Okay. So this you got. Now you consider the first term. X You can just change the okay. So why I can change all those things? Why I can change the order of integration? Who will tell me? What type of theorem I have used?
Fubini's theorem.
Huh?
Green's
Which theorem?
theorem.
I just what I am saying that whether you do first integration 0 to infinity or minus infinity same. So what type of theorem I am recalling now? Which theorem? You haven't studied measure theory?
Fubini's theorem.
Have you heard the name Fubini's theorem? Have you heard the name Fubini's theorem?
Yes, sir.
Then why you don't know what is the Fubini's theorem? Then you have to check whether the integration is finite. What are the conditions for applying the Fubini's theorem? Anyway, I will not say anything. Apply Fubini here. Fubini's theorem I apply. Okay, so I can whatever integration order you take, no problem, no matters. Of course, you have to check why I can use Fubini's theorem. Okay, good. Now you know I can use the integration by parts. Do you know the definition? You know what is the integration by of parts, or that also you don't know? If I use integration of parts in this term, what will happen? Can you tell me, or you don't? You don't know. Do you know integration by parts or not? Yes or no? You have to tell me. Yes or no? Atharva, you know what is integration by parts?
Yes, sir.
What will happen to this term if I do integration by parts here?
Sir, I think one term will gain the.
What I not this is mathematics. I think no. What will happen? Tell me.
Sir, UVT minus.
This will happen minus infinity to infinity, 0 to infinity. You change, there will be a minus because I shift in the derivative here. Uxt ddt of v and the boundary term. That means what is the bound at 0 and at infinity? So what will be the boundary term? Huh? This minus infinity to infinity. What will be the boundary term? What will be the boundary term?
U of x0, v of x0.
Exactly. U of first is u of x infinity v. So what will be this term? What is ux at infinity? Huh? I say infinity. What will be v of x infinity?
Okay, I found this on the web for infinity. What
will be v of x infinity? I said so many times that
0.
It has a compact support. So it is 0. V at x infinity is 0 because V has a compact support. You see the compact support is in this space, r cross 0 infinity. Okay? Anyway, it is 0. So another boundary term will come minus infinity to infinity, ux at 0, vx at 0. So this part is over. So what will be this part? If you do the integration by parts, so x will come. So minus infinity to plus infinity. The boundary terms will be v at infinity and v of minus infinity, both are 0 because v has a compact support in x as well. Okay, so that will be 0 to infinity. It will be minus infinity to infinity f of u v at x dx dt, that is equal to 0. So finally you will obtain minus infinity to infinity 0 to infinity u of xt dt of v of xt dt dx minus infinity to infinity 0 to infinity f of u vx dt dx plus minus infinity to infinity ux of 0 vx of 0. Okay, so you will obtain this. Okay, so if you multiply this equation with vxt and integrate, so you will obtain this. Okay, this is equal to 0 because this is equality. So this left hand side is equal to this part, and you know right hand side is 0, so you will get 0. Okay, now can you get any idea how to define the solution? So the definition now, this is just a motivation. So the definition is like this, I will define. Okay, we call any bounded, measurable function uxt as a weak solution to that PDE weak solution if it satisfies this condition 0 to infinity minus infinity to infinity u vt plus fu dx dt minus infinity to infinity ux0 dx for all v belongs to cc infinity of r cross. See what have I done here is the following. Here we know that we assume that, let us assume u is a smooth solution. Okay, then only I can throw the derivative. I can write the derivative ut like this, right? Ut plus this, I throw the derivative to v, or fu I throw the derivative to v, because v is smooth, you know. Anyway, you know v is smooth, but here already we have assumed that ut is also smooth, right? Pointwise sense. So I can do the integration by parts and throw the derivative to v. Here also I throw the derivative to v because we know f is a smooth function. That is why, right? So now if I say that in this equation u is a solution, but u is not smooth. U is not smooth. Not even continuous. Or just not even continuous. Then how I can write derivative of del u by del t plus f of u derivative of x at equal to 0? This I cannot write in a pointwise sense. You can understand this means this is not a meaning of pointwise sense. Because for defining the pointwise sense, we have to know that u is a smooth function. At least the derivative of t exists, u of with respect to time exists, derivative of f with respect to x exists, and all those things. Okay. So here the pointwise sense I cannot define the solution. So what I do here, just with this motivation. The motivation is, suppose first of all you assume that u is a smooth function. Okay. Then what I have did, and I say let us multiply this equation with a smooth function, and then by integration by parts I have throw the derivative here. I throw the derivative to this function. Okay. Now I call it, and this if I throw the derivative, the conclusion is here. Here see, u, after throwing the derivative u and fu, we don't require to be a continuous or anything, right? We just define this. For this integration to exist, do we require f to be smooth or something? Because I have, if the derivative is in v, only I require that this integration should make sense. This integration should make sense, and of course you should define at least at u at x0 at should define. Just we need that u at the point 0 should define. That's all. Because what I have done is I throw the derivative to the v, which is a smoother version. Okay. Now with this motivation, I will call a function u is said to be a measurable if this makes sense. Forget about the integration by parts. This is just a motivation part. What I did here, I just defined it like that. U is said to be a measurable, not even continuous. Measurable function is a weak solution to the PDE if u into Vt, that integration should make sense. If you just for all and integration should make sense. You know L1 function, L2 function sense. In the measure theory you have studied what is an L1 function, one is L2. So everything the derivative is along t, derivative is along x, and of course ux comma 0 we should define pointwise sense ux 0. That's it. All other I don't need anything. So u is a measurable function is said to be a weak solution if u into Vt plus fu Vx in the sense of integration. After integrating should be equal to minus infinity to infinity ux0 vx0 for all v, not for any particular v. This equality should hold for all v in CC infinity function. The idea is we throw the problematic part to the smooth part. Okay, this is the idea of weak derivative. Okay, so we call this is a weak solution if all the integration makes sense and for all v belongs to CC infinity. This equation, this is an equality. Clear? Is that clear to all? This is very important. I can wait 1-2 minutes. Please tell me. This is a very new concept of solution. Should I repeat?
Sir, could you please repeat?
Good. See, again I start with this. For this equation to study this, you know that suppose I got a solution u which is not smooth. Okay, so I cannot write in this fashion ut at the point xt, fu at the x at the point xt. We cannot write if u is not a smooth solution. Agreed? So you in the each step you should say yes or no. Otherwise I will not understand where you have not understand. Okay? Agreed? If u is not a smooth solution, you cannot write this equation in a pointwise sense. So I have to say, so you got a u which is not a smooth. Okay. Now let us suppose u is a smooth solution. Let us suppose. Okay. Then ut at xt, f of u at xt makes sense. Makes sense or not?
Yes, sir.
Okay. Now what I did multiply with this equation with a function v of xt, which has a compact sum, and integrate. That makes sense. What I did here. Makes sense?
Yes.
Okay. Now v is also smooth, u is also smooth, everything is smooth here. So I can use the integration by parts. Yes or no? Yes or no?
Yes, sir.
Integration by parts. What I did integration by, I throw the derivative to v, I throw the derivative of x to v. Because s is a smooth function, u is also a smooth function, everything makes sense. Okay. So this equation, if I multiply this, right hand side is 0, so 0 is equal to this. Yes or no? Yes or no?
Yes, sir.
Yes, sir. Now the question is, now if you see after integration part, is there any derivative involved in u or f? No?
No, sir.
Yes or no?
No, sir.
No. Now with this motivation, I will call now, because this integration part is just giving you motivation how to see the three things. Now I will say that we call any bounded measurable function uxt as a weak solution of this PDE with this PDE. If this integration holds true, if this equality holds true for every v in CC infinity. Agreed? This is a definition, and you can now you have to tell me if u is a smooth function. Are you getting if u is a smooth? then is the weak solution coincide with the classical solution? The question is, if U is smooth function, then whether weak solution is a classical solution? Huh? Tell me. If U is a smooth function in x and t variable and f is also smooth, then you tell me then whether this is the weak solution coincide with the classical solution? Yes or no? Yes or no? What is the meaning of a classical solution? That means you should satisfy this PDE in a pointwise sense. Of course, U of x0, you know hx. Anyway, tell me.
Sir, for U to be a classical solution, it will need to be continuous. But the weak solution, I don't think that they will be continuous.
That if U is a smooth function, so if U is smooth, then also I can define this equality. Yes or no?
Yes, sir.
I say that U is a weak solution. On the top of that, I also assume that U is a smooth function. Okay. Now I am saying that whether weak solution coincides with a classical solution. Yes or no?
Yes, sir, we can get back the same equation, like same PDE back. So I think yes, sir, because we can reverse the same process and get back the PDE.
What we can do? What I cannot hear you. Please again.
Sir, reverse the process. Just what we done, we can reverse the same process and get back our original PD, and from there we can conclude.
What we will do is U is smooth, then throw the derivative in, do the integration by parts. Do the integration by parts. If you do the integration by parts, if U is smooth, then only you can do the integration by parts. Otherwise, no. Here I assume U is smooth. That is why I throw the derivative here. Now the question is, I have assumed U is smooth. Then I can do the integration by parts, right? If you do the integration by parts, you will end up with this. 0 to infinity ut plus, just check, p of xt dt dx equal to 0, and this equality holds for every v in cc infinity of 0 infinity cross r. Okay, you know u into phi equal to 0 for all phi. This is a major theory question. For all v into cc infinity, this infinity of this, if omega, this imply u has to be 0 almost everywhere. But here almost, because u is a smooth function, so almost everywhere will be. So this integration into v equal dt dx equal to 0 for all v in cc infinity function. This imply ut plus f of ux equal to 0 almost everywhere. But we know that u, fu, everything is continuous. This means this imply ut plus fu x equal to 0 for all x and t. Okay, so this implies u is a smooth solution. Have you studied this property in major theory? If integration u and phi equal to 0 for every cc infinity function u equal, so this is an exercise. You try. U is a smooth function. Then u is a smooth, is a classical solution. Okay. Okay. So if u is a smooth, then weak solution coincides with. So the answer is, if u is smooth, then weak solution coincide with classical solution. Is that clear or not? Agreed, all of you? Atharva, Ankit,
Yes, sir.
Annu, Vishwa, Chitram, Deepak, Dev,
Yes.
Dilkhush, Ekans, Gitanjali, Govind, Kritika,
Yes, sir.
Manish, Mano, Minakshi, Nikita, Nirmal, Sanjeev, Shami,
Yes,
Vivekananda.
sir.
Yes, sir.
Yes, Sanjeev. Agreed?
Agreed, sir.
Yes, Sanjeev?
Agreed, sir.
Okay, good. So this is the definition of weak. This is I understand. When I also studied first time this dictionary, it makes me what is happening. So the problem, this is the motivation. At least I said you the motivation that if is a smooth, then you arrive at that equality, right? So now use this idea to define something new, and that is the I define here everything. There is no. This is called the weak solution of the PDE. This. Oh, I forgot to write. Ut plus f of u x equal to 0, u at x0. Okay. Okay. So this is uxt is just a measurable function, bounded measurable function. Okay. We call a bounded measurable function is a weak solution of this PDE if this equality holds true for all v belongs to C infinity of r cross 0 infinity. Clear? And then I prove that if u is a smooth function, then a weak solution coincides with a classical solution. That's good. Okay. Now come back to the problem. Okay. Now this is a very nice theorem. Let's try how much you understand. Let's see. If uxt is a weak solution, of this equation, ut plus f is any continuous function. Okay. Okay. Such that uxt is discontinuous. Is given that u is a weak solution, and given that uxt is discontinuous across the curve I will draw the picture and I will tell you what is that x. But u is smooth on either side of the curve. I will tell what is d minus and d plus, everything I will tell you. Then uxt must satisfy the condition that x prime t is equal to f of u minus f of u plus. I will tell what is u minus u and u minus is the limit of u from d minus, and u plus is the limit of u from d plus. Okay. So what is given? So this is f of xt. Let's say again x belongs to R, t positive. Okay. Okay. It's a weak solution given, and also given that uxt is discontinuous across the curve uxt, some curve, but u is smooth on either side of the curve d minus and d plus. What is that? Draw the curve. This is your domain where you are solving the PDE. This is your x. This is your t. Clear? So there is a curve. in the xt, which is the curve x equal to xt. So it is given that this is the solution to the uxt is a weak solution of the. You know what is the meaning of that? That means this is the meaning of that. That means this. That means uxt satisfies 0 to infinity minus infinity to infinity u vt is this that. Okay, and it is given that u is a smooth function here. D minus means you take d minus is this part left side and d plus is this. So this you understand d plus d minus. You understand d plus d minus. Okay. So either side of the curve d minus and d plus. Then uxt must add. What is u minus? U minus is this. So u minus is nothing but limit x going to the curve x from this left side. Okay, you understand? So u is smooth here. U this is u minus. Here if you go, this is u minus. This is u plus. If you go from this, clear? Is that clear? U minus is the limit of u from d minus. So u minus is the limit of u from where x belongs to d minus, and u plus is limit of x going to xt oblique x belongs to d plus u of x. Clear? Yes or no? Clear or not?
Yes, sir.
Clear? So there is a curve which, let's say, partition this in two parts, d minus and d plus, and in one part it is u minus is the limit of u when it's coming from d, and of course there is a discontinuity along this curve. So u minus is not equal to u plus. Okay, I assume it, and such that uxt is a discontinuous across the curve. Okay, then the question is, then if such thing happens, if u has a discontinuity along the curve and u is a weak solution, then some condition, some necessary condition has to happen. Okay, the necessary condition is x derivative at time t, the tangent at any point of the curve, the tangent should satisfy fu minus fu plus by u minus. This will have to satisfy. This is necessary. This is a necessary condition. Okay, if u is a weak solution to the PD in this domain, and u has a discontinuity along this curve, that means u minus and u plus are not equal. Okay, then if u is a weak solution and u has a discontinuity like this, then any curve will not work. That curve will work for which the x prime of t satisfies this. This is a necessary condition. Okay, is that clear? Is that clear? So any arbitrary curve will not work. Then you should satisfy, and x prime t will satisfy this equation. Is that clear?
Sir, means we are basically trying to find the curves on which this is possible.
Yes, exactly. You want to find the curve for which this is possible. What is possible? U is a weak solution and U has a discontinuity along the interface of this curve. Exactly. So any arbitrary curve will not work and any arbitrary U will not work. So this should satisfy, the curve should satisfy this property. Is that clear? Statement of the theorem is clear?
Yes, sir.
Yes? Okay. Let's prove this. Very simple. The proof is very simple. Just you have to use that U is a so D minus let D minus is this such that 0 less than t and minus infinity minus x less than x. You know what is the meaning of D minus and D plus. And also you know that U is smooth on either side. That means here U is smooth, here U is smooth. Just a minute. I will call you later, please. I will call you later. So here it is u is continuous, here u is continuous. Only problem is u minus is not equal to u plus. U minus is, you know, the limit of this, and d plus is 0 less than t less than infinity, xt less greater than x. Clear? Okay. This is, and assume ux at 0 is 0. That means I have assumed that hx is 0. I assume this. We will see later. If don't make it complicated, ux is equal to 0. Okay. Now tell me, in d minus, and also u is a weak solution. What you can do now? So u is also a weak solution in d minus. Agreed? If u is a weak solution in the whole domain, then u is also a weak solution in d minus, or not? What? What happened? What happened?
Yes, sir, it will be.
So this is d minus u vt. Just write down the definition of weak solution. F of u vx dt dx is equal to, you know what is that, minus infinity to what is that, xt, u at x0 v at x0 dx. But this is 0 because I have assumed ux is 8 is 0. Agreed? Agreed or not? For every v in cc infinity of the curve. Agreed or not? What happened? Draw the picture. D minus is this. So this is D minus. So what are the boundary of D minus? This is the boundary, and this is the boundary. Right? Yes or no?
Yes.
So what are the boundary on this domain D minus? This is the boundary. It can go up to infinity, and this is the boundary. Agreed?
Yes.
Agreed or not?
Yes, sir.
Okay. So this is 0. Now you know that here, and you have taken some compact set somewhere, some compact set like this. V is the compact support in whole cc infinity of R cross this. Okay. Now you tell me, for all V in cc infinity of this. Okay. Now you know that in D minus, U is a smooth solution. U is smooth. U is smooth. Okay. In D minus, U is smooth. Agreed? In either side. U is smooth on the either side of the curve, D minus and D plus. So over D minus, U is smooth. Agreed?
Yes.
Yes or no, bhai? What I can do now?
Sir, we can replace v by u minus.
What I can do? I can throw the derivative to U by integration by part, because U is smooth in D minus. Agreed? So this is equal to, this integration is equal to minus D minus UTV. Okay? Yes or no? Yes or no?
Yes, sir.
Yes.
Okay. What is the boundary term? Huh? Because I am throwing the derivative, so boundary integration by part, the boundary term will come, right? What happened? What is the boundary term? Tell me, what is the boundary term? What is the boundary of D minus? Tell me. This is the boundary. Huh? This is the boundary. And what is the value of the U at the boundary? In this boundary, what is the value of U?
0.
Tell me, Baba.
0, sir.
Huh? 0. So this boundary will not come because u at x0 is 0. So only this boundary will affect. Yes or no? So this is x equal to xt. The boundary term only with this. This is the boundary term. xt u. What will happen? U minus the bound. What is the value of? So this is the unit normal. Eta 1, eta 2. The outward unit normal at any point. And at any point, what is the value of u at the point xt? At the point xt, when I am coming from the left hand side, what is the value of u? U minus into mu eta. Understand? Yes or no? Yes or no? You don't know integration by parts, right? If I am not wrong, you don't know what is integration by parts. Tell me honestly, do you know integration by parts? Huh? Do you know what is integration by parts? Huh? Yash, Athar, Ankit, Deepak, Sanjeev, Shammi. What is integration by parts? You don't know. Yes or no? You have to tell me, yaar. Please tell me yes or no. Do you know the integration by parts or not? Huh?
Sir, we know, but what is this mu eta 2, sir? This thing is not understand.
What? Huh?
So what is this, sir? Mu eta 2, sir?
You don't know.
No, sir.
You just tell me this. You don't know. I will teach you. What is in this? It's not saying anything. How can I understand that you know or you don't know? Okay. Now let's see. Let's do this. Next class I will tell you what is integration by parts. Okay, in a very brief way. Okay, clear? The boundary part with the outward normal. Okay, N2, the outward normal. Okay, this is the, and if we do this integration by parts of this, you will get this again. Will get integration d minus f of u x v dt dx plus x equal to xt u minus, sorry, v minus, we will get, sorry, fu minus v nu 1. Okay, nu 1. This is the surface measure. This measure of this curve ds. You understand? This part you understand. Everyone understand. I throw the derivative, right? You have to tell me yes or no. Otherwise, I can't. Then I don't know how to go forward.
Yes.
So when I throw the derivative, you know. But the point is, you don't know how to tackle with the boundary term when it is a R2 or R3 space, right? In R1, you know, right? If I am not wrong, is
Yes,
that the way?
Yes.
Yes, sir.
Right? The problem is when you are applying in Rn or R2, you don't know why this type of new one is coming, the boundary term and all those things, right? Anyway, you assume that this is the outward normal u minus, and this is v. Okay, this is, you just assume this, and then I will tell you later. Okay, so if I do the integration by parts, finally I can write down like this. This I will make you understand in the next class. Integration by parts of this integration. U pt plus fu dx dx dt. By integration by parts, I can write this like this: minus d minus utb plus fux v dx. The boundary term is x equal to xt. This curve this is x, this is t, this is xt. This curve, this is your x equal to xt. So the boundary of d minus is this curve and this curve. Here u is 0, so nothing will come. F of u also, I assume f of u will f of 0, f of u at x0 is 0. That means f of 0 is 0, I assume. Okay. F of 0 is 0, then only this comes with, in this part nothing will come. This part. So the boundary, only this boundary part will come into play. And this will get u minus v eta 2 plus f of u minus v eta 1 and the measure of the boundary. Here is eta 1, eta 2. Okay? So this you understand. This part you understand. You don't understand this part. Why these boundary terms come? Right? Am I right?
Yes.
Yes, sir.
Am I right? Okay. So for the today's talk, please assume that there should be some. Just think about the one dimension. When you do a to b, f g prime, what you do? You do minus a to b. You throw the derivative of with f g, f prime g, plus you write down f b g b minus f a g. Right? Yes or no? This is the boundary. So this boundary part corresponding to this. Okay? At least you should understand this much. Okay?
Yes, sir.
Here everything is one dimension, so you can't see what is happening. Okay? So at least I will write down the thing. It's very difficult to prove the integration by parts in RN or somewhere now. So at least I will tell you the motivation, how to do it in RN and all those things. You should have done this in measure theory course. Anyway, I will tell you in the next. So this part corresponding to the boundary. Okay. This is why this minus comes, because see like this A B. So the outward normal here is 1, here is minus 1. You understand? So that is why this minus comes. FA into GB, F at the point the boundary. What is the boundary point A? FA GA into the normal. This is the normal new 2. This is here the outward normal is minus 1. You understand? And here the outer normal is plus 1. One direction you fix plus, another direction you fix minus. Okay? So this is B, so this is plus 1. That is why here no. Now you understand, that is why new 2 and new 1 comes. This is the unique normal. So in RN or in R also there is a unique normal, but we take this to be a plus 1 and a minus 1. You understand? At least little bit you understand?
Yes, sir.
Okay. Now similarly, I can do similarly in D plus. In D plus what I can write? Again same thing. D plus UVT plus FU Vx dx dt, okay, is equal to D plus. Again I can throw U is smooth in D plus. So I write U D plus U at T plus F of U at x point x V dx dt, and again the boundary x equal to xt. Now we are coming from the bound. Just draw the picture. So this is your xt. So d plus ac. So this boundary again no problem. This 0. The boundary term will come. Now what is the value of u at the boundary xt? You know, at this boundary from right hand side, the value of u is u plus. Okay, that I will write as u plus v eta 2 plus f of u plus v of eta 1 ds. Agreed? Huh? Agreed? Yes or no?
Yes.
Yes, sir.
Yes, sir.
Okay. Now by the assumption ut plus f of ux equal to 0, this is a weak solution in D minus and in D plus, and we know that u is smooth, then what is this value in D plus? U is smooth in D plus, and also you sat in D plus, you satisfy ut plus f of ux equal to 0. So what will the value of ut plus fu in D plus? Huh? U is a smooth
0.
function and you satisfy pointwise sense this equation. Now we have this equation and u in D plus, and the equation is in D plus, and you know that u is a solution in D plus and u is smooth. So this is pointwise sense, it is 0. Yes or no?
Yes.
Yes, sir.
Yes. Here also the same thing. In pointwise sense this is 0. Pointwise sense it is 0. Okay. So both are 0. So what will happen? And also it satisfies this equation. So what I will get? What will happen? This part should be equal to this part. Agreed or not? Huh? Agreed or not? U is a weak solution, so this part is 0. This part is 0. Now I am saying that this is equal to this. Yes or no? Yes or no? This is the 0.
Yes, sir.
This is 0. Also this is 0 because it's a weak solution. This is a weak solution. This is 0. So both should be equal. This equal to this, and this is also 0. This is also 0. So what left? What is left?
The boundary terms.
Exactly. Only left is the boundary. This implies we have x equal to xt u minus v eta 2 plus f of u minus v eta 1 ds is equal to x equal to xt u plus v eta 2 plus f of u plus v eta 2. Because UTFU equal to 0 in D minus and D plus. Agreed? Clear?
Yes, sir.
With solution. That means this is equal to 0. This is equal to 0. So 0 equal to, so equate 0. That means this is equal to this. Now we know that this is equal to this plus this. But here it is 0. Here also it is 0. So only left is 1. Okay? So this holds for every V in CC infinity of R cross 0 infinity. Okay? So these imply x equal to xt u minus eta 2 minus 1 minute plus f of u minus eta 1 minus u plus eta 2 plus f of u plus eta 2 into v ds equal to 0 for every v. So what I can say, this implies major theory, this property, that for any u into phi equal to 0 for all phi in CC infinity, then u equal to 0. This is your function into v equal to 0 for all v in CC infinity of R cross 0 infinity. Huh? So this implies what this implies? Huh?
This will be 0.
0, exactly. U minus eta 2 plus f of u minus eta 1 is equal to u plus eta 2 plus f of u plus eta 2. Okay? So this implies, if you check, this implies u minus eta 2 plus f of u minus eta 1, that is equal to u plus eta 2 plus f of u plus eta 1. Okay, and if you do this, minus eta 2 by eta 1 is equal to f of u minus f of u plus by u minus plus. Okay, but we have to prove this is equal to x prime t. How to prove this? Okay. So what is your curve? X equal to xt. So at any point on the curve is how it looks like xt comma t. Yes or no? Okay. X prime. What is the derivative? What is the tangent to this curve? Now, this is what is the tangent to this curve? Gamma prime t is x prime t comma 1. Okay, the normal eta 1 dot eta 2 should be equal to 0. Agreed? Eta 1 dot eta 2 equal to 0, comma. This is a component of the normal. Eta 1 and normal is a two-dimensional eta 1. So x prime t eta 1 plus 1 dot eta 2 equal to 0. So x prime t is equal to minus eta 2 by eta. Agreed? Yes or no?
Yes.
Yes or no? Agreed?
Yes.
Yeah. Yes. Okay. So we obtain x prime of t should satisfy if this is the solution f of u minus f of u plus by u minus plus. So this is our statement of the theorem. So provided when this will happen, if u is a smooth on the either side, at second u is a weak solution, all of the plane u is a weak solution, and second u has a singularity, has a discontinuity across the curve. So this time this is t, this is your x, this is the curve x equal to xt. So you have a here you have a thing. So the thing you just think, remember when we said that the two characteristic intersect, that means you have a problem at this point where it is intersect. Yes or no? Yes or no?
Yes, sir.
So you have a problem. So this type of problem, that is why we define this type of curve. Okay, we have a problem whenever there is intersection. That means there is a discontinuity here. We see that whenever the characteristic intersect, u has a discontinuity at those points. So this is the curve. So suppose u has a discontinuity along this curve, then if u is a weak solution, then this will satisfy. Agreed? Understand, all of you? So only thing you did not understand is this. I hope this integration by parts. You know this integration by parts. At least you should understand why I have written this eta 2, eta 1 and all those things. ठीक है? Correct?
Yes.
So next class I will explain you what is the main issue in the idea. I will not be able to prove this because it will take 2-3 classes. I can't waste improving. I cannot waste improving the integration by parts for 2-3 classes. Okay, I don't have such freedom. But at least I will make you understand. At least I will tell you I will write down what is the formula exact, what is the integration by parts, and at least I'll tell you some example and some motivation. Okay. Of course, the motivation comes from here. One dimension. Yes. Okay. So this much. So just one or two more thing. So this is the thing. So in notational way, sometimes people write remark. In notation, it is written as follows. In notation, it is written as follows. This third bracket u is u minus u plus. F u I write down as f of u minus f of u plus, and sigma I write down as x prime. So the condition is f of u. The previous condition is sigma u times. People write in the book this is called ranking Huganoid not RH condition, or sometimes it is written RH condition. This is very important. Ranking Huganoid condition. Okay. Now I will tell you, once you have this ranking Huganoid condition, next remark I will just a minute. Once you have RH condition, we could using this RH condition, we will be able to find character. We can able to produce characteristic and a weak solution. We could able to find characteristic curves, curve, and you will see, and will produce weak solution. Like this case. So you have a intersection for every S positive, S negative. Everywhere there is an intersection, right? So you have the discontinuity along all curves, along this characteristic curves, right? Yes or no? So we don't know how to define solution here. Of course, the solution is not a classical solution, but is there any way I can define here? No problem. Here there is no problem. You can define it. So I will do like this. Here no problem. Then for every S positive there is a problem. So somehow we will define something, some characteristic, so that there is no intersection. Using RH, we will see how we will do that using RH condition. You understand why we are studying RH condition? We will see that this RH condition will help us in defining solution whenever there is a intersection of characteristics. Okay, you understand? In the next class, I will do how to define solutions whenever there is a intersection of characteristics. That means whenever there is an intersection of characteristics, that means you have a discontinuity, right? So we have to make that part. We will define a new curve which satisfies the RH condition, and so that the U is a weak solution. You understand? All of you? You will see.
Yes, sir.
We will produce 3 examples. All those 3 examples, wherever we have a problem in defining solution. Okay? We will do the 3 examples, and I will show you how we will define a solution on those points. Okay? Okay. So next class I will do. So next class I will do examples. How to apply examples. How to apply RH condition. Okay? This I will do. And second, I will explain integration by parts. Very short. Integration by parts. If you don't understand, at least you should understand the statement of the theorem. That's all. Okay? Integration by parts in a small way. And finally, this is the last class before your exam, that first quiz one. You can ask me your doubts. Okay? I will see if you have any doubts. I will try to clear. Okay. Is that plan okay?
Yes.
All of you? Yes.
Yes, sir.
That is yes. Yes has left. Anyway, so please tell me honestly, are you following the class? Please tell me honestly. Are you able to follow the class? Athar, Anu, Pritika, Sanjeev? Huh?
Sir, there
Ekant?
was a problem because of integration by parts because we did not have a clear idea how to use that in RN. So
Okay. At least now you understand what is integration by parts. Huh?
some idea
Something?
I got. Yes.
Some idea. So next class I will write a very general statement. Okay, I will not able to prove because I cannot waste 3-4 classes. Okay, so it's a very long proof. Okay, so at least I will give you the idea and how to use this in some problem. Okay, and try to tally with your one dimension case. So this integration by parts formula I will use every time from the next chapter. Now and then. So you have to understand, at least you should understand the statement of the theory. Okay, clear?
Yes, sir.
Okay, very good. So we will meet on Saturday to follow it up, and on Monday we will have an exam, and I will send you the link, all the instruction tomorrow evening. Okay, clear? Thank you. Thank you. Thank you.